Our networks are comprised of various devices, and these devices provide the core services and capability that allow our network to work. Each device has its own function that allows data to get from our workstation out to the internet and back. So let's take a look at some of the key devices that make up a network. The first device we're going to look at is the modem, which stands for modulation and demodulation. Modulation simply means the process of combining a carrier wave and a modulating wave. A carrier wave is the sine wave that is used to attenuate a signal to a certain frequency, and the modulating wave is the signal that is being applied that has data. So combining these two, we turn a frequency carrier wave into a wave that now carries information. And the modem can create these signals and it can deconstruct these signals. So it does its own modulation and it does demodulation on received signals, and it converts that demodulated wave into data that is then sent inside of your network for your switches, routers, and other traditional networking equipment to deal with. It's in a form that they can handle. I don't want to go too deep into signaling theory here, but it's important for us to understand some fundamentals about how data is sent from device to device at the physical layer before it gets to a more logical data-centric approach where we're talking about IP packets and protocols. Looking at the top image, there's a very, very simple diagram of a signal of when it's being turned on, it's broadcasting or sending some form of information, and when it's off. It's not sending information like you would think. It's represented in either off 0 or on 1. So the speed at which this signal can turn on and off dictates how many zeros and ones can be sent. The sending device and receiving device, before they start sending legible communications, go through a process called synchronization. This involves sending a preamble, which is a pulse train like this, what we're looking at, on and off, very simple signal, but they send the signal at defined or well understood durations, and each system receives these preambles, which is simply a train of an on-off signal state, and they use that to synchronize their clocks. And when they do that, it allows the devices to then sample the signal accurately when additional intelligence and data starts coming in. The problem with a waveform like this, being able to send just an on and off, works well for slow data rates, but we need to be able to send data faster and more reliably. That requires multiple channels of signals being sent simultaneously. So let's talk about QAM, or quadrature amplitude modulation. QAM is the primary signal that's used in modems. It's also used in 802.11 wireless. It's used by mobile providers to provide data flow to your device from their wireless network. But again, what makes QAM really powerful, and this being a 16 constellation-based QAM, is that it has two signals. We can see in the diagram on the bottom right that we have two signals that are interlaid with each other. And you can see that they offset each other when they're broadcasting. So it's two signals consuming the same frequency or the same general carrier signal. However, what they do is each sending device and receiving device transmits and senses on a phase. So they use phase to sample these different points when these sine waves or the carrier waves are modulating. To better illustrate what phasing is and how it's being used to send and receive data simultaneously between two signals, to better understand phase, think of the face of a clock. 12 being at the top of the clock, 6 being at the bottom, 3 to the immediate right, and of course 9 being to the immediate left. So when we overlay this QAM constellation on a clock, we can see the QAM will send signals or sample signals at various points on the face of that clock. We see samples at 12 o'clock, roughly about 1:30, 3 o'clock, 4:36, 7:39, looks like 10:30 and 12. But there's also two signals being transmitted here. We see that inner ring, which is 8 points, and then the outer ring that's 8 points. So even though these two signals are consuming the same carrier frequency, they're broadcasting at different amplitudes and they're being measured at different phases of the transmission. So that way we can physically separate these different data points so they're not interfering or they're not overwriting the data or information on another signal. Furthermore, what makes QAM so powerful, and a lot of more modern signaling systems do this, is that each of these constellation points don't simply represent a 1 or a 0, they actually represent a byte or a bit of data, depending on how big these constellation gets. A 16 QAM is very small. We have 128, 256-bit constellation QAM, so much, much larger signaling. But each of these points on that face of the clock there that is being sampled represents more than just a 1 or a 0. It might represent 4 zeros and 1. A next constellation point might be all 1s. And every combination that we could create having 16 unique points. So a QAM that has 32, 64, 96, 128, the more points you have, the more combinations of 1s and 0s you can send. And here's the purpose to that. Each of these data points is not sending any data at all. There is no 1s and 0s being actually sent. The recipient and sender both know that if I measure on the outer amplitude band at noon, it's 0101. So we didn't need to send 01 or 01, which would take longer and require more signaling. We just know if we sample amplitude at that point at the right time, it just means 0101. So the receiving computer just creates the data out of nowhere. It just measures a point in time and space from the signaling that it received and says, well, if I sampled a signal here, it means these many bits. So we're able to send these little fast pulses of amplitude modulated signal, or these amplitude and phased modulated signals, and the receiving and transmitting just know what those points in time and space mean. We don't actually have to send the raw data. And this is also why it's very important to check the integrity of files that you download. When you download something from the internet, you're not actually being sent that file. You're being sent a constellation of measurements. Amplitude and phase on an X and Y axis is being interpreted into 1s and 0s. The raw 1s and 0s were never sent over the wire. Your computer is literally reconstructing a file based on a diagram of a constellation. So let's talk about the router. We've all heard that term, or most of us should have heard that term by now. We all have what we would call a router at home, but one thing to know is that a router is a very specific function in the network. It can be a physical appliance, it could be a software implementation, but at the end of the day, it's a set of network functions. It's a part of a network operating system that does some very specific functions that allows the transmission or routing of packets. And that's what we need to remember when we think of routers. Routers route packets between dissimilar networks. So when we go back and think about ARPANET and the early internet, what made that network hard to scale was that everybody had to use the same protocol and everybody had to manually set up connections between every facility. That's just simply not scalable. We can't bring in new people quickly because we have to adopt their protocols, they have to adopt ours, we have to run the cable, everything has to be manually set up. So we needed devices, we needed scale, we needed protocols that were designed to allow this communication. And that's what a router does. It routes between dissimilar networks. It standardizes the form or the language that we speak when sending data over a network. Routers are one of the true boundary devices to a network because they implement what's called access control lists. And just like they may sound, an access control list is a listing of approved connections that can be sent through the router, both from the public internet to our internal network, or from our internal network out to the internet, or even between two private networks that we might manage internally. ACLs allow us to essentially whitelist, these are approved, or blacklist, these are not approved. Routers work by sensing their peer routers around them. They use various protocols and algorithms to identify these routers, and they assess the cost of the link. And what we mean by cost is, what is the cost or impact of sending data over one connection vice another connection? Many routers actually know multiple ways to get to the same destination. There might be 4 interface connections to 4 other routers, and the router could send your data to any one of the 4 peer routers. However, because it's using various cost estimation algorithms, at that point in time, link 1 has less network congestion, and it's able to get packets to the peer router faster. So this is what routers are doing all the time, is they're assessing the quality of links and ensuring that our data gets through the most efficient path. And this is what's very interesting about the internet, is that even though you might have one established connection to a website or you're downloading a file, your data is not always being sent through the exact same path. you might go through 4 or 5 routers to get to your destination, and there might be a few routers that change over the duration of your connection simply because something occurred that caused the link or the cost estimation of that connection to be higher than an alternate path. So the router would send the next packet to the appropriate destination. And that's the power of routers and in using the internet protocol, which you're going to learn about later, is the fact that our data can be sent over multiple unique and distinct links and all get to the destination so that we can collect and reconstruct the data that was initially sent to us. Routers maintain what are called routing tables, and these are simply entries that record the cost estimations, which are referred as metric values that we'll see here in a moment. And these metric values are recorded for the router to make decisions on where data is going to be sent. So if we sent a packet to a router saying, I would like to go to google.com, it's going to check its route table and verify what is the lowest cost to get this packet to its intended destination. So here's an example of a route entry, the source being another router. So this is information that it gained for another router. And that router told it, hey, if you want to get to any destination that's associated with this network, this 172.16.4.0/28, that describes a whole range of IP addresses. And we're going to learn more about what that IP address means as it relates to the size of that destination network. Next, we have the administrative distance. And what's interesting about administrative distance is that each protocol that are configured to be used over a routed network have their own distinct administrative distances. These are predetermined values that essentially put weight on how much a link costs or what its efficiency is to send data. Some protocols are better than others. Not all protocols were created equal, and many of the protocols are designed for a unique purpose or a unique configuration of a network. So because these protocols are designed for unique purposes, they each have a unique administrative distance which articulates how well they perform at a certain function. The metric is the router's assessed costs. So this is the receiving router looking at this route and making a cost estimation on how efficient this link is. So if our router receives a packet that's destined for that destination network, it then knows, hey, I need to send this packet to this next hop address at 209.165.200.226. That router knows how to get to my destination network, and I know it's a good link to send because it has a low metric value. The route timestamp lets us know how long it's been since we've seen that route, or we've assessed the quality or efficiency of that route. And the outgoing interface is the interface that the router will use to communicate with that next hop. There are many routing protocols. Some of them are used for internal routing, while some are optimized for external routing. If you're interested in learning more about these protocols and how they're configured, you might want to look at the Network Plus certification or taking a CCNA class. They have a whole module, nearly 40 hours of content that is just on routing protocols and configuring and managing routers and switches. So the next device we have is a switch, and it's called a switch because it certainly doesn't route packets, but because it actually switches data from one interface to the next. So if we can think about old telephone systems, when you used to pick up the phone and talk to an operator, that was referred to as a switch operator. They would create circuits to send data from one phone to the next, and that's exactly what a switch does. It uses a store and forward method, which essentially means your device is connected to a switch, your computer, a laptop over a wired connection, and it sends out an Ethernet packet or an Ethernet frame to the switch, and the switch receives that Ethernet frame and denotes, this physical port just sent me an Ethernet frame. It then stores that frame in memory and then opens up a path to the recipient physical interface and then flushes that data from memory, that Ethernet frame, and sends it to the recipient device. So it doesn't do routing. Routers, like we just saw, make cost estimations, they assess the network. They do a lot of algorithmic analysis to determine the best way to get data there. A switch essentially looks for a collision in the network to ensure that there's nobody talking on a path, and then just sends the data out once it's been validated that it's clear to send. So that memory I talked about is referred to as the content addressable memory, or the CAM table. So the CAM table is used to store which devices are connected to what interface. So if you have the little router you have at home, if you've ever connected a device in using an Ethernet cable, as soon as you plug that device in, your device's network interface card talked to the switch and said, hey, it's me, this is my MAC address, and the switch said, cool, you're connecting to port interface 1, I'm going to store in my CAM table your MAC address. So if anybody in this network tries to send a packet to your MAC address, I will store it in memory. I will then send that data to your switch interface. So the switch is just simply very quickly creating circuits between all of these physical interfaces as fast as it can go, and it has a little bit of memory to buffer the data it's receiving from each of these interfaces, and then simply transmits over the next interface when it has time. One thing to note, even though we talked about routers primarily using the IP protocol, they still use Ethernet. Most routers use an Ethernet cable to connect to a switch. A switch has to be able to talk to a router, and the only way that's going to occur is with an Ethernet frame. So when you send a packet out to go to google.com, your computer creates an Ethernet frame, sends it to your switch, and the switch recognizes that this Ethernet frame is not destined for the local network. So its default approach is to send it to the router, which is referred to as the default route. If a user's trying to send data to a host that isn't in the current network, it defaults to try to send it out to the network and let the router decide where it needs to go. The router will then receive the Ethernet frame from the switch, and if we recall, the process of encapsulation will start peeling off the layers. It will start peeling off the physical layers, the MAC address, and it's looking for that layer 3. It's looking for that network address, the IP address. And once the router gets that network address, it then says, yes, I have a route in my route table. I can forward or route this packet to an appropriate destination. So what the router does is then encapsulates the data into a new IP packet and then sends it out the door.